Hello guys, welcome to another video tutorial. In this video, we are going to solve the problem number 15 and so on, depending on how much time we have today, but I try to solve more problems. Anyway, so let's start. Here is the problem 15. The magnetic circuit for a saturable reactor is shown in this figure. Here we have this core and two coils. You can see the direction of the current for the coil 1 and the coil 2. The BH curve for the core material can be approximated as two straight lines as shown in this figure. This is the BH curve of the material and we should use it to solve this problem. So let me copy this. Here is the structure and we have this BH curve for the core material. As you can see, when the value of H is equal to 400, the value of the B is 0.8 Tesla. And when the value of H is equal to 1000, the value of the B is 1 Tesla. So this is the knee point, and this is the saturation zone. Actually, before the knee point, the value of the permeability is high, but for this zone, yes, we have reduction in the value of the magnetic permeability. So it is obvious here we have 600 rise in the value of the H. Okay, so 1000 divided by 400 is equal to 2.5. So the value of H for this point is 2.5 times the value of the H for this point. But here we have a little increase in the value of the B. Okay, so this is the saturation zone. Anyway, the aim is A, to calculate these quantities, the value of I2. So let's check. A, if I1 is 2 ampere, the value of the current for the coil 1, calculate the value of I2 required to produce a flux density of 0.6 Tesla in the vertical limbs. So the value of the current for the first coil is given. The aim is to produce 0.6 Tesla in vertical limbs. How we can solve this problem? So here we have these two coils. You can see the direction of the current for the coil 1, the direction of the current for the coil 2. So the field that is generated by the coil 1, the flux is in this direction, and the flux that is generated by the coil 2 is in this direction. So we can draw the equivalent circuit of this structure. Consider that the width of one vertical limb is different from the horizontal one. The width of a vertical limb is 1.5 centimeter, but the width of the horizontal one is 1. Okay, so we have different reluctances for vertical and horizontal limbs. Here you can see the equivalent circuit of the structure that we have here. R1 is the reluctance of one vertical limb, and R2 is the reluctance of the horizontal one. This is the magnetomotive force for the coil 1, and this is the magnetomotive force for the coil 2, that is in this direction. You can see the polarities of these sources here. The value of the flux density for a vertical limb is given here. How we can calculate the value of the flux density for a horizontal limb? So the value of the flux density is 0.6 Tesla for this limb and 0.6 Tesla for this one. How we can calculate the value of the flux density here for this horizontal limb? We know that the value of the phi is the same for vertical and horizontal limbs. So we can write phi is equal to B1, A1 equal to B2, A2. B1 is the value of the flux density in a vertical limb, B1, and A1 is the cross section here of a vertical limb, and A2 is the cross section of a horizontal limb, and here we have B2. So we know the value of B1, we know the value of A1 and A2. We can calculate B2. So the value of B2 is equal to B1 times A1 divided by A2. Dimensions are given here. The depth of the problem is also 1.5 centimeter. So here, yes, also you can see these equations for B1, B2, and this ratio. So we can calculate the value of the B2 using this equation. This is the first step. Here is the code for the problem 15. We have this H data, B data. This is our HP curve. So let me run the code here. This part of the code. You can see the HP curve I constructed, also the negative part of the HP curve, this part, because later we need it when we use the F0 function. So, okay, here is the value of the current for the coil 1, 2 ampere, the number of turns for the coil 1, the number of turns for the coil 2, the depth of the problem 1.5 centimeter. This is B1 0.6 Tesla, and this is A1, the cross section of a vertical limb, that is equal to the depth of the problem times W1. W1 is the width of a vertical limb, this one. This is W1, and this is W2. that is 1. So we can calculate A1, A2, and finally we can calculate B2, flux density in horizontal limbs. So if I run the code here, you can see the value of B2 that is equal to 0.9. So we found this number. The value of the B2 is zero point 0.9 Tesla. So if we are going to have zero point 0.6 Tesla for vertical limbs, the value of the B for horizontal limbs will be equal to zero point 0.9 Tesla. How we can calculate the required amount of the current? We can use the equation, right? This equation, integral of h dot dl equal to summation of magnetomotive forces according to this magnetic equivalent circuit. This equation, and in this equation, instead of B, we need H. How we can calculate H? Using interpolations, right? You can write the equation of this line and this line and find the value of the H for the corresponding values. So here, when the value of B1 is 0.6, the value of H1 is 300. 0.6, 300. And when the value of the B2 is zero point 0.9, H2 is 700. So when this is 0.9, this is 700. Just equation of these two lines, you can write the equation of these two lines and find this number. Also, here in the MATLAB code, I used this function, the one-dimensional interpolation. We have B data and H data, and the value of the B is known. We can calculate H. And finally, we can calculate the value of the I2, right? According to this equation, I implemented this equation here. This is the value of the I2. So when we know the value of H1 and B1, we can plot the operating point. So let's run the code. What is the value of the I2? As you can see, the value of the current is negative of 2.5. So the direction of the current is in this direction, 2.53 ampere, right? We supposed this direction and write the equations, but finally we calculated this number. So the negative sign means that it is in the opposite direction. So here in this plot, when we run this M file, you can see these 2 points. This one is for the vertical limb. The B is 0.6 Tesla, H is 300, and this is for a horizontal limb. The B is 0.9 Tesla and H is 700. Okay, these two operating points that we have here. As you can see, the flux for the vertical limb is before the knee point. This is the knee point. But the horizontal limb in the saturated zone. Okay, so you can see these two operating points. So now let's solve the part B. If I1 is zero point 0.5 ampere and I2 is 1.96. Calculate the total flux in the core. How we can solve this problem? We should use a trial and error method. Neglect magnetic leakage. Yes, we neglected magnetic leakage when we generated this equivalent circuit. So for solving the part B, like before, like what we did for the previous example, we can define error and use the f0 function. So here in this case, I am going to define this error. This is the error that I am going to consider. So we have a BH curve, right? That is like this. This is our BH curve. And we define this error. When the error is equal to 0, this equation, integral of h dot dl equal to summation of ni, is true. So we can confirm that we have found correct values for h1 and h2. How we can define a single variable function to calculate the error and solve this problem? I can consider this error function, and this time instead of instead of h that we considered for the previous problem when we considered the error function, I am going to consider b1 as the variable that we use for the function that is used for the f0. So here, if we consider b1, an arbitrary number here, right? This is b1 or b1 star. We can calculate h1. Yes, h1 is calculated using one-dimensional interpolation, right? Interp1 using the value of b1 star. And the value of b2 is equal to b1 times a1 divided by a2. We know this fraction. And finally, we can calculate h2 again using one-dimensional interpolation function, interp1. And finally, we know the value of n1 i1, n2 i2. We know the value of h1 h2 and l1 l2. Finally, we can calculate the error and then try to reduce the value of the error by changing the value of the b iteratively. What is the value of L1? L1 is the average length of flux line in a vertical limb that is equal to this one. The L1 is this, the average length of flux line in one vertical limb is this one, that is equal to 6 plus 1, that is 7. So here is the next M file, problem 15b, part B. The value of the L1 is 7, and the value of L2, mean length of flux path in horizontal limbs, is 7.5. That is 6 plus 1.5. This length. So, yes, here we have these inputs. This is A1, A2, and here I use this F0 function to find the root of this error function. Here is the error function. The input, the variable is B1. So we calculate B2, and then we calculate H1 and H2 using one-dimensional interpolations, and this is the error. We know that when the error is 0, actually we have found the operating points. So let's run this code. Here, as you can see, we calculated the operating points for the vertical limb. The value of the B is 0.8, and for the horizontal one, the value of the B is 1.2 Tesla. And we have this high value for the magnetic field intensity. So as you can see here, the value of H for the horizontal limb is 4 times the value of H for the vertical limb, but we don't have much increase in the value of B. Okay, so we actually are in saturated zone for this structure. These 2 points, the value of the flux density for both vertical and horizontal limbs. So, okay, how much is the value of the total flux in the core? We can calculate total flux using this equation. You know, the phi is equal to B1 A1 or equal to B2 A2. I implemented these two equations here. After finding the solution B1, we can recalculate B2, H1 and H2. Then we plot the operating points, and finally we calculate the flux in the vertical limb and in the horizontal one. We know that the amount of the flux, right, is the same. So when we run the code, you can see the phi1 and phi2. That is equal to 0.18 milliweber. Here you can check the number that we have here in the reference, 0.18 milliweber. And the value of the current for the part A is minus 2.53. We calculated it in this M file, the value of I2. So, okay, this is the solution procedure for the problem 15. You can repeat that. Let's go for the next problem. Problem 16. A toroidal core has a rectangular cross section as shown in this figure. It is wound with a coil having 100 turns. The BH characteristic of the core may be represented by the linearized magnetization curve of this figure. So determine the inductance of the coil if the flux density in any part of the core is below 1 Weber per meter square. Okay, below 1 Tesla. So how we can calculate the inductance? The first point, inductance depends on saturation level in the core, is not constant. So this is our assumption. If the value of the flux density in any part of the core is below 1 Tesla, how much is the value of the coil inductance? How we can calculate that? So let's copy this figure. Here is the problem. For the material, when the H is 100, B is 1 Tesla. When H is 400, B is 1.2. So if the level of the flux density is below 1 Tesla, the operating region is actually this line. Yes. So let's consider the red color is this line. So because the level of the flux density is below 1 Tesla, we can consider a constant permeability, right? For all of these points, this is just a line. We can calculate the slope of this line, that is the magnetic permeability. The slope of this line is equal to 1 divided by 100. Yes. So we can consider this permeability and calculate the inductance. Either we can use the magnetic equivalent circuit method, or we use this formulation. We discussed this formulation before for this example. Yes, for the problem 10, we discussed this formulation. Here, the cross section is rectangular, and you can calculate the total flux in the core. And finally, the coil inductance is lambda divided by I, or N times phi divided by I, that we have this equation. In this equation, R1 is 4 centimeter, R2 is 12. Here we have diameters. Okay, so here we have these diameters 8 and 12. If you consider this as z axis, this is the cross section of the coil. This is R1, this is R2. These are diameters, 8 divided by 2, 12 divided by 2. This is 4, this is 6, and this length is L is equal to 3. You can use the integration method that we discussed before and calculate the total flux passing through this area. That is equal to this one, and this is the coil inductance. So here I implemented the equation. This is the minimum core radius, the maximum core radius, The core permeability for the part A of the problem, the number of turns is 100. The coil length is 3 centimeter. So this is the value of the inductance. The depth is in centimeter. We need to multiply it by 1e minus 2. So if I run this code, as you can see, the value of the inductance L coil is 0.19 henries. So let's go for the next part, part B. Determine the maximum value of the current for the condition of part A. What is the condition of the part A? We need to keep the level of the flux density for all parts of the core below 1 Tesla. So how much is the maximum value of the coil current that this condition is true? How we can find that? Okay, let's draw this plot. In the problem 10, we generated this curve. This is B as a function of R. Here we have R1 and this is R2. This blue curve is the variation of the B. So here, in this case, we have this variation for the B. This is R and this is B. This is R1. This is R2. So this is the variation of B. We know that we have maximum B for minimum radius and we have minimum B for the maximum radius. So when we increase the level of the excitation, the amplitude of the I, we have, right, higher values for B. Actually, the value of the B is equal to this. We discussed it before. This is the value of H and B is mu times H. So when we increase I, we have higher values, right, for the value of the B. So if we are going to keep the value of the flux density for all part of the core below 1 Tesla, so we should consider this. Suppose this is 1 Tesla. The value of the B for R1, right, must be equal to 1 Tesla. In this case, we can confirm that the value of the B, right, inside the core for any part is below 1 Tesla because the maximum is for R1. So here we have these two equations. Okay, H is Ni divided by 2 times pi times R. So the maximum value of the current is equal to 100 times 2 times pi times R1 divided by N. According to this HB curve, okay, this is the HB curve. And as you can see, when the value of B is 1 Tesla, the value of H is 100. So for B1, we should set the value of H equal to 100. Then we can calculate the maximum current, right? That we can confirm that any part of the core is below 1 Tesla. How much is that? So let's run. This is the value of I max, 0.25 ampere. So, part C, determine the minimum value of the current for which the complete core has a flux density of 1 Tesla or greater. Yes. So if we consider this, if this level be 1 Tesla for the B2 for this position, if the value of the flux density for the outer surface of the core is 1 Tesla, we know that this is the minimum value, and for any point, right, any radius lower than R2, the value of the B is higher than 1 Tesla. Again, we can write this equation, this one, but in this case, the value of the R is R2. Yes, the value of the H when the B is 1 Tesla is 100, and we consider this case. In this case, we use R2, and what is the value of I mean is 0.37. So we have these two numbers. When the value of the current is below this number, the inductance of the coil is equal to this one, right? Because any part of the core, the flux density in any part of the core is below 1 Tesla. And in this case, when the value of the current is higher than this one, we have a saturated core. Any part of the core is saturated, and the flux density in any part of the core is higher than 1 Tesla. Okay, so you can redo the calculations, right, and derive the numbers for this problem. Let's go for the next problem. Problem 17. Okay, so here we have problem 17. A coil wound on a magnetic core is excited by the following voltage sources. We have two cases. For the first experiment, we apply 100 volt. The frequency is 50 hertz, and for the next one, we apply 110. This is the RMS value of the voltage. The frequency is 60 hertz. Compare the hysteresis losses and eddy current losses with these two different sources. For the hysteresis loss, consider n equal to 2. So in the reference here, in the section of hysteresis curves, we have these two equations. When we consider a sinusoidal excitation, two equations are explained for calculation of the hysteresis loss. Yes, this equation, the hysteresis loss is equal to kh, the coefficient, times the maximum level of the flux density to the power n times frequency. So this is the equation to calculate hysteresis loss of the core. And in this equation, the n is given equal to 2. So if we consider n equal to 2, we can compare the ratio of the hysteresis loss for the second experiment and the first one using this fraction. So here we have pH2 divided by pH1 is equal to this one. So, is the value of KH constant or not? KH can be a function of temperature and other quantities, but here in this problem, we don't have any information and we consider it as a constant. So if we consider the value of KH constant, we can write this equation. And the ratio of hysteresis losses is proportional to the ratio of frequencies, right? The power is 1, and the ratio of the maximum flux densities. But in this problem, the maximum values of flux densities are not given. We have voltages. Also, you know that we have this equation, right, for sinusoidal excitation. Here you can see the equation of the voltage in this part, sinusoidal excitation. If we consider this flux in the core, the induced EMF is N times derivative of the flux is this one, and this is the maximum value of the voltage, the peak value of this induced voltage, or in terms of RMS quantities, we have this one. The RMS value of the voltage is 4.44 times N times frequency times phi max. So here we have this equation, and instead of B max, we can use E divided by this part. So if you replace this equation, instead of B max 2 and B max 1, two cases, finally we have this equation. So the ratio of hysteresis loss is proportional to ratio of voltages to the power 2 and the reverse of frequencies, F1 divided by F2. So you can replace these numbers, and as you can see, the ratio of pH2 divided by pH1 is close to 1. We don't have much difference, right, in the hysteresis loss for these two operating conditions. But what about the eddy current losses? We have this equation for calculation of the eddy current losses. This one, the eddy current loss is equal to Ke B max to the power 2 times F to the power 2. So again, you can consider this fraction, replace the value of B max. Finally, we have this. The ratio of eddy current losses is proportional to E2 divided by E1 to the power 2. So if you replace the numbers, as you can see here, we have 21% increase in the value of eddy current losses in the second experiment in compared with the first one. So let me check the numbers here. Yes, you can see these two numbers in the solution. So yes, you should remember these three equations. This one, this is a well-known equation, important one. The equation for calculation of hysteresis losses and eddy current losses. Here we considered the value of Kh and Ke constant. Okay, so now let's go for the next problem. Problem 18. Okay. A toroidal core of mean length 15 centimeter and cross-sectional area of 10 centimeter square has a uniformly distributed winding of 300 turns. The pH characteristic of the core can be assumed to be of rectangular form as shown in this figure. The coil is connected to a 100 volt 400 hertz supply. Determine the hysteresis loss in the core. So, how we can calculate hysteresis loss? The hysteresis curve is given here. So, as you know, the energy lost by the hysteresis loop is equal to the area of the hysteresis loop. But we don't have any information of the hysteresis loop inside, right, this rectangle that we have here. So let me copy this, paste it here. We have this hysteresis loop. Let's review this concept. When we have a coil core system and we have a sinusoidal current in it, this is the trajectory, right? You can read the hysteresis part of the chapter 1, and as you can see, this is the magnetization curve, the normal magnetization curve. So we have these hysteresis loops depending on the maximum value of the B that we have. In this problem, the RMS value of the voltage is given, the frequency is given. Also, we have the dimensions of the core, the mean length and the cross-section area. So we can calculate the volume of the core. So the RMS value of the voltage is equal to 4.44 N phi max times the frequency. This equation, you can calculate the maximum value of the B. The maximum value of the B is equal to E divided by 4.44 NFA. And if you replace the numbers here in this equation, we will have this number 0.188 Tesla. But here we have this hysteresis loop. So how we can solve this problem? The B max that we calculated is equal to 0.188 Tesla. I can consider this normal magnetization curve according to this figure and the explanation that we have in the chapter 1. And consequently, if we consider this normal magnetization curve, we can consider these hysteresis loops depending on the level of the excitations that we have. So we have different loops. For each level of the B, we can calculate H depending, right, on the level of the excitation. We have the equation of this red line. The equation of this red line is B equal to the slope of the line times h. How much is the slope of the line? Is 1.2 Tesla divided by 10. This is ampere per meter. So considering this Bmax and equation of this normal magnetization curve, this red line, that is this one, we can find the value of h. So we have the value of B, that is 0.188 Tesla. We can calculate the value of the h, that is equal to 1.566 ampere per meter. And how much is the total energy loss in the hysteresis loop? We should calculate the area of this loop, that is equal to 4 times Bmax times Hmax. This equation, this is the total energy loss, the area of the hysteresis loop. 4 times Bmax times Hmax, that is 1.177 joule. And finally, you know that the hysteresis loss is equal to the volume of the core, the energy lost in the hysteresis loop times the frequency. You can replace the dimensions. The volume of the core is the mean length times the cross-section area. Here the unit is centimeter. We should convert it to meter. And the area is centimeter square. We should convert it to meter square. This is the energy lost and this is the frequency. So we have this amount of loss, hysteresis loss for the core. Okay, so this equation is explained here in this part of the reference, hysteresis loss. You can read these equations, the procedure for calculation of the hysteresis loss, this equation 1.31. This is a really good reference, right? Good explanation of these important concepts. This is the equation. If we have the hysteresis loop, we can calculate the total energy lost. And if we have the volume of the core and the frequency of the excitation, we can calculate the hysteresis loss as we did in this example. So the important point of this problem was the normal magnetization curve that we should consider. Okay, so now let's go for the next problem, problem 19. Here the core in figure 17, this figure is available in the chapter, has the following dimensions. The core cross-sectional area is 5 centimeter square. The mean magnetic path length is 25 centimeter. The core material is silicon sheet steel. If the coil has 500 turns and negligible resistance, determine the RMS value of the 60 Hz voltage applied to the coil that will produce a peak flux density of 1.2 Tesla. So the maximum value of the B, the flux density is given, and the excitation is sinusoidal. The frequency is given. We have this equation, right? This is the RMS value of the induced voltage, 4.44 NF phi max. The resistance is negligible, so this is equivalent to the RMS value of the applied voltage. We don't have resistive drop. You can consider this, the phi max is equal to the area, cross section area times B max. You can replace the numbers that we have here, the number of turns 500, the excitation frequency that is 60 hertz, cross section area we should convert it to the meter square, and the maximum level of the flux density, this one 1.2. Finally we will have this value 79.92. This is the RMS value of the 60 hertz voltage applied to the coil. Okay, just we used this important equation. You should remember this equation for solving the problems of this chapter and the next chapters. We will use this equation also for induction motor, synchronous motor, transformers. Okay, an important equation. So let's check the solution here for the problem 19, 79.92, the same number that we calculated here. Okay, I think the time of this video is high, so you can repeat solving these problems, practice, and let's continue in the next video. Thanks for watching.